Welcome back to another episode of Double E's Talk Tech, our third in a series about quantum computing. My name is Mike Hoffman.
I'm Daniel Bogdanoff, and with us we have Lee Barford. He's our quantum computing guy here at Keysight, and we've had a couple fascinating conversations with him. Mike and I are really excited.
It's really nice to have a quantum computing guy. I mean, if you don't have a quantum computing guy, find one.
You should get one.
Yeah. Well,
It's a good
one
guy to
of the quantum computing guys.
So quantum computing, the basic, my understanding, or parallel computing rather, is more or less sharing clock cycles between different processors. Is there, is that a gross oversimplification? Or
I think it was a good description of the common state of practice a few years ago. When processor clock rate stopped increasing, the response of the microprocessor manufacturers was to increase the number of usually identical processor cores on a CPU chip, and so that would be what you describe, and the programmer would have to figure out how to break an algorithm or program up into multiple tasks, multiple processes that could run on those multiple processors. However, a development that's been becoming more important over the last half dozen years is the increased use of specialized processing elements integrated on the same, either separate or integrated on the same part. So use of GPUs, of graphics processors for general computation, is an example of that. The GPU is a completely different kind of processor from an x86 or an ARM. And tuned for very different kind of workloads. Right, a GPU is very good at matrix math, vector math, graphics processing, and image processing, since that's what they were initially designed for.
So it's designed for pixels, basically, right? So if you have this array of pixels,
initially designed to manipulate pixels, but if you look at those algorithms, they involve a lot of floating point computation to decide what to draw. Basically requires modeling what you want to draw and having numeric algorithms that will generate those pixels. So the pixels are small integer values, but behind that you need it's convenient. It's extremely convenient to have at least single precision floating point. And it was discovered that you could do all sorts of floating point calculations, particularly ones where you had a number of identical operations that you wanted to do at the same time. Just like you have to do a lot of, you have to generate every pixel in an image, in parallel to put it put it into the frame buffer and display it. You need to. There are lots of other algorithms in other areas, from physics simulation to machine learning, that are similar in that gross description, and GPUs are good at those. GPUs were external daughter cards predominantly. Now, in the last year or two, the GPU manufacturers are starting to release low power parts suitable for embedded application that include several traditional cores and a GPU. Now you can build embedded systems that say take advantage of machine learning algorithms that would have required too much processing power and too much thermal power. Too many volts times amps for an embedded system, and now you can build those on these processors. Now that's an example of a hybrid processor. Hybrid means that it's got two very different kinds of cores in the same part, And the task
Okay.
of the software architect or of the product architect is to figure out which workloads in the product belong um, on which kinds of
Sure.
core.
Yeah.
There's a professor named Andrew Chen at the University of Chicago who has been predicting for a number of years that that's a trend that's going to accelerate. That in order to fight against the difficulties caused by um, it becoming harder and harder to get advantage out of semiconductor feature size shrink, um, that future processors will have more and more kinds of specialized cores, will be hybrids
Okay.
of more and more kinds of processor. Um, and there's some indications that we'll see the first processors this year, next year, that have three different kinds of processing element on
Hmm.
board, each tuned to a different kind of workload.
Interesting. So what would the three different kinds be? Like,
Well, I
or
think
maybe what are some differences in? So we talked
so.
about GPUs and
Yeah. So well, I mean the traditional processors are tuned. Traditional processors are tuned for algorithms that are algorithms on integer and floating point operations where
Mhm.
there is not a great deal of advantage to doing more than one thing at once because there's short dependency chains. What you're going to do
That
next, or
makes sense.
the data you're going to operate on next, depends very intimately on what went just before. GPUs
Sure.
are good at things where you can find enough operations that can happen simultaneously because there are not these super tight dependencies. Um,
Okay.
However, neither kind of processor is very good at extremely hard real-time processing. Um,
Okay.
if you get down um, if you have real-time constraints where the latency um, between when you sample something with a analog to digital converter and need some sort of an answer back or decide whether or not to do something or whether to loop back or get more data in a few microseconds or less.
Hmm.
Um, no kind of microprocessor or GPU is very good at that because the
Right.
operating systems themselves impose latencies and timing jitters um, in the dozens of at least in the dozens of microsecond range, and then so you need some other kind of digital hardware
And
to
that's
be
why
able
we've
to.
been seeing so many people. We've talked about this on previous shows. We brought in some of our ASIC team. Is we see a lot of people designing custom ASICs to handle that type of real time analytics, but
Yeah,
those are focused on very specific tasks. It's not so much a general purpose thing that you can just plug and play
right. But
around with.
FPGAs,
So
for example, fill that gap.
yeah, that makes sense.
Right?
Okay.
They have an intermediate in every way that I can think of. They're intermediate between um, CPU traditional CPUs or these hybrid CPUs, either way, and the and building ASICs. Right, so
Hmm. Okay.
they're intermediate in the amount of engineering effort. They're intermediate in time to market. They're intermediate in the amount of flexibility, and they're intermediate in their real time performance, both in terms of um, throughput and also in terms of timing jitter.
Okay.
Right.
So are quantum cores something we could see at some point?
Our
Like I don't
quantum
know,
core
like
is
in the next
something we
100
could see
years?
at some point. Yeah, I mean, in if in consumer products, um,
Well, so
even the
maybe
most
there's
pessimistic
consumer product
estimate,
talking to a
even the most pessimistic estimate of building quantum computers that would be would be able to exceed the performance of current computers, um, in but in a in isolation, in some kind of, in a building with a laboratory with a controlled environment. The most pessimistic of those is 50-year estimate. There are
Okay.
other real experts, full professors at top 10 universities in the world, who will say that's more like 10 or 15 years. So what you're really
Okay.
asking, though, is when could that be made into a consumer product? To be a consumer product, it would have to be have to be something solid state.
Okay.
Those physical technologies at right now seem to be more speculative, but there are physicists out there who have them and are experimenting with them. So yeah, it would be
Okay.
absolutely conceivable in a century, or possibly even quite less. You can see it's
Okay.
conceivable that in 20 years you could have quantum core, quantum solid state quantum core on a hybrid processor. Given how fast technology
Okay.
moves, I'm not going to say it's impossible. Would I bet my own money? Would I bet my own money on it? Not so sure.
Sure.
The crazy thing about quantum computers, as it is starting to dawn on me here, is that up until now, technology has always been an evolution of improving previous known. This is like a whole new thing, right? This is like
Yeah.
reinventing how we think about computing.
It's like the
And-
transistor.
Yeah, so it's not like, hey, we're going to have quantum computers that are right out of the gate going to perform just as well as today's computers. It's like clearly not the case whatsoever, right?
And not only that,
mean,
they're going to do different problems. They Although in theory you can do anything with a quantum computer that you can do with a conventional computer, it's not necessarily going to make a lot of sense to do so. There are many problems where it's not at all clear that they would be any faster and could well be much slower
Yeah.
than a conventional computer built on current digital CMOS technology. There is a catalog on the web, though, of dozens to hundreds of problems where at least people have published papers that say, here is an algorithm for thus and such a problem on a quantum computer, and the performance could well be substantially better, or would be substantially better than on today's conventional computers, under a number of assumptions that may or may not pan out at the end.
Okay.
People are creating algorithms for things that don't exist yet. That's some real high level math right there.
Yeah. Well, I mean, there wouldn't be the billions of there wouldn't be the $1 billion. The British business magazine, The Economist, several months ago estimated the total spend on quantum technology research, most of which is quantum computing research, to be over $1 billion a year, both from government and private sources, worldwide. That's a worldwide number, and a huge proportion of that, though, is generated by the promise of the algorithms in such papers, starting with probably with Shor's factoring paper that we discussed in an earlier episode. So a lot of the interest is driven by that promise, but it's not a promise to be a kind of processor that completely replaces current processors.
Interesting. So I'm almost getting so it's clearly quantum computing is in almost like a speculative phase right now, or are researchers and scientists pretty confident that this technology will work? Or is it like
it
nuclear
depends on
fusion,
who you talk to.
Right?
Well, you talk to a professor who's raising...
not nuclear.
Yeah.
I'm sorry.
You
Sorry,
you
go ahead.
talk to a professor who's raising money for his startup, and he'll tell you it's a sure thing, right? Um,
Yeah.
No pun intended. Yeah.
my opinion, and I think this is a fairly common opinion, is that it's still very speculative, but
Okay.
the upsides are so great um, that neither the incumbent computing and internet companies they don't want to be left behind. If somebody gets a breakthrough, they don't want to be
Mm-hmm.
left behind. Neither does any industrialized country want a breakthrough to happen somewhere else and they get left behind.
Sure.
So there's enough
So
promise that people are
yeah.
worried about that risk and are willing to spend big bucks to avoid
So the promise, yeah, the
yeah.
promise is not just to like Intel or to some big. I'm just picking names. I don't know enough about the industry to get myself in trouble. Or the U.S. government. It sounds like the funding and the interest is pretty, cross sector, cross country. Is that accurate to say, or
It's certainly cross
are there a couple
country.
industries?
It's certainly international. I mean, if you look on the web, you can find these long white papers from the U.S. government, from the EU government, from the UK government, for example, all laying out the quantum research strategy for their respective country or bloc,
Okay.
and they're backing those up with research investments from their science agencies. There's also VC money out there. I mean, if you look just in today's in my inbox came an email from one of my colleagues saying, "Look, here's a B round that's been announced for such and
Mm-hmm.
such a startup." And they have to be making a pitch to their VCs. They can't be telling their VCs it's going to be 50 years, right? They have to be telling their
Right.
VCs that they're going to build something real in a small enough number of years that the VCs will fund them. So they clearly are people who think they're closer
Venture
to
capitalists.
reality.
Yeah.
Is all this research and development are they coming from competing interests, or is everybody sharing their knowledge for the greater good to advance this technology? Because it sounds like if there's VCs and money involved, it's becoming
Yeah.
proprietary information and trade secrets, this, that, and the other.
So it's a mixture. There are the startups are very much in I don't want to say stealth mode, because at least a couple of them are are public about certain aspects of their work. So for example, they have software components that they're open sourcing, and you can just go to GitHub and download them. And they'll say they have certain bits of physics working, but when they go and if you look at their YouTube videos, the micro photographs of their bits of physics have certain portions thoroughly smeared out. So they're being open. They're trying to generate interest, but they're keeping their trade secrets. They want to maintain their competitive advantage. And there's other work though, which is purely academic. There's other work which is purely academic, where they publish their papers, and there is no apparent there are no apparent secrets being kept. But
Sure,
it's very much a
that makes
mixture.
sense. So we're running a little low on time. Is there anything else in the quantum or the parallel computing space you want to cover before we start to wrap up here?
I think I had the say on that.
Okay. Yeah, it sounds like it'll be really interesting to see how quantum computing, how different types of computing play into different needs that we will have as individuals and companies, and the implications on security and autonomous cars. And we have a running joke on the podcast that everything always comes down to space lasers. It sounds like vacuum
lasers are
well,
clearly part of this. I'm excited.
Quantum communication, which we didn't talk about, absolutely comes down to space lasers. You just look at the Chinese have a satellite that they're using. So we talked about quantum computing, but there's also the similar kind of idea of using quantum effects, engineering with quantum effects, to build things that don't appear to be buildable without them. And those include quantum communications, where you can send photons with entangled states. In other words, they both have almost one probability of having the same state or opposite states. And the Chinese have a satellite where they can generate these entangled photons and send them to two different base stations on the Earth. And then so if you send random ones of those, you've sent a random number. And if anybody else reads them, that will be detected as a feature of the quantum mechanics. You can detect because the wave function will collapse prematurely.
Yeah.
So that's quantum communications. There's also quantum sensing, where people use other quantum mechanical effects to potentially build accelerometers and gyroscopes that are orders of magnitude more sensitive than those available today. So we talked about quantum computing. The real possible future here, though, is that engineering with quantum effects becomes a new field of engineering, a new specialty within engineering. Quantum engineering is a new field, and just like electrical engineering was born around 140 years ago. Electronics engineering was born out of it, maybe call it 70 years ago or so. Computer science was born out of a combination of math and electrical engineering about 70 years ago. And those are were the births of new engineering disciplines. We may be sometime, it's quite possible that sometimes during the last 5 years or the next 5 years, people will point to as the birth of quantum engineering, with many different applications, not just quantum computing.
So I'm gonna start wrapping us up, but I feel like quantum communication is like date night when you're not sure what restaurant you're gonna go into. You're not actually sure where you're going until you pull up at the door of the restaurant, and you're like, "Oh, okay,
we'll just go there."
Yeah. Okay, so I think it's time for a stupid question from Mike. I'm gonna put you on the spot.
Yeah. Okay. What's your favorite quantum state and why?
Oh, what's my favorite quantum state, and why?
I sense a trend in Mike's questions.
my favorite quantum state is called the Bell state, and that's that's the one way to think of that is that's the equal probability state between 1 and 0. It has other interesting properties as well, but it's the commenters in the below will say, well, there's lots of things you need. There are lots of fundamental things, but to me, it's the Bell state sort of encapsulates in one tiny snippet of math a lot of the weirdness that's going on here.
Well, I know what I'm doing for 3 hours later today. It's browsing Wikipedia, reading about quantum states.
Yep. And I believe there is a Wikipedia page called Bell State, and it's not a bad place to start and work out from.
Well, there you go.
Down the rabbit hole we go.
Yeah, I have a 12-hour drive to Texas tomorrow, so I'm gonna save that to my phone. All right, that's all we have time for, Lee. Thank you again so much for being on our podcast. And Mike Hoffman, co-host as always, and I'm Daniel Bogdanoff. Make sure you subscribe to the Keysight Oscilloscope's YouTube channel. Check us out on your favorite podcast engine and give us a review, especially iTunes. That helps us out a lot. If you like this podcast, let us know. If there's topics you want to cover, put them in the description. We will see you next time.
Okay.
Thanks.
Great.